So there are really two big ideas in DC electrical circuits that we have to worry about, and they're listed down here below. The first one is that matter is conserved. You already know that, but it has implications for the circuits that we set up. In particular, the circuits that we set up involve electrical charges moving around. And when we say matter is conserved, we're talking about the conservation of electrons, basically. This circuit you've already seen, I'm going to reset it up and watch it run, has electrons in it. These little dots represent electrons. Of course, there's Avogadro's number of electrons, or roughly that, instead of the, I don't know, 50 or 60 that are shown here. But conservation of matter tells us something. It tells us every time an electron runs into this battery, an electron on the other side runs out. So every time an electron runs through any point, as written down here, any circuit element or even a single point, if I look at the electrons coming in here, if an electron comes in here every 2 seconds, then an electron goes out of here every 2 seconds. You know, of course, by now that the current that we define, capital I, is going in the opposite direction. The electrons are running counterclockwise here, and because they're negatively charged, we define the current as running clockwise around this circuit right now. So that's the first big idea, and I can expand that idea a little bit by changing the circuit around. If I change it around like that, you can see that there's two things going on. The current right here is equal to the sum of those two currents. There's some of it going this way, some of it going that way, and the total current coming into this point equals the total current going out of this point. So let me go back to what I had. If I can. Two resistors in a row. The second big idea is that energy is conserved. Now, you already know that, and we've talked about it a little bit, how it works for electrical circuits, but I want to write an equation that makes it a little more explicit. And before talking about that equation, I have to point out that we're going to talk about changes in energy, and so we're going to pick two locations, 2 points in this circuit. I could pick a point just to the left of the battery and a point just to the right of the battery, or I could pick a point just to the right of the battery and a point in between the two resistors, or what we'll do a lot, I could take a point here as one of my points. Think of going all the way around the circuit and coming back to the same point. So pick the same point for the 2 points. So after you pick 2 points, then energy conservation tells us that the change in energy per unit charge between those 2 points is just equal to the energy per unit charge you've added minus the energy per unit charge you've taken out. As the current goes from the low voltage side of the battery to the high voltage side, the energy goes up, so energy is added. This is the EMF of the battery, whatever the rating of the battery is in voltage. The current is going clockwise, so every time the current goes through a resistor, then energy per charge is taken out, and that's just the current times the resistance. When you say taken out, the energy is not thrown away. Taken out just means the electrical energy gets changed to internal energy in the resistor. This resistor is heating up because current's going through it. This battery is adding energy because it's a battery, but of course you know that it also has an internal resistance, so it is also heating up a tiny bit. So those are the two big ideas. Energy is conserved and matter is conserved. The way I've set up these two resistors is that they're in series. We call it series because they're wired so that Conservation of matter demands that they have the same current. Every time an electron moves into this one, an electron moves out of that one. Same is true of the battery actually here. So all three of these circuit elements are in series because they all have to have exactly the same current. I'm going to put 3 resistors in series. So how do we use conservation of energy here? They all have the same current. Let's go around the circuit clockwise because that's the direction current goes. That's the easiest way to do it. Let's take a loop around the entire circuit. So let's start over here on the right of the battery. Take one loop around the circuit and come back to this point. So we'll go around like that. As we move through the battery, energy is added. So we have E battery. As we continue around the circuit, the current is of course clockwise, so the energy is taken out by this first resistor. I've written that as minus I1R1. If I call the current through the second one I2, then I have a minus I2R2 as I continue around the loop. And as I continue around the loop, there's one more resistor, minus I3R3, and then I get back to the starting point. So delta V around the entire loop is equal to 0. I started here on the right, went all the way around. Around that loop, I found a battery and 3 resistors. Of course, we've already talked about the fact that that conservation of matter means that the current through these resistors, they're wired in series, the current has to be the same. And so I don't need to call them I1, I2, and I3. I can just call it I, in which case I can factor that out. Because this is 0, I can solve for E battery. And I find out that E battery is I times the sum of the resistors. And I can call that an equivalent resistance. Equivalent resistance just means if I took these 3 out and put in only one resistor, if that one resistor had the resistance equal to the sum of those 3, and I had the same battery, then I would get the same current. That's what equivalent means. Another way to wire together resistors is in parallel. Let's see if I can set that up without. Two resistors are said to be wired in parallel if they're wired so that conservation of energy demands that they have the same voltage drop across them. So same voltage drop. How do I manage to get the same voltage drop across two circuit elements, or 3, or whatever I decide to do? The way I'm going to do that is by connecting them with a wire. So what I've done, the right-hand side of this resistor is connected by a wire to the right-hand side of that one. Same wire to the right-hand side of this one. All 3 resistors have a wire connected between them. As you know, in good conductors, there is a negligible voltage drop across a good conductor, in other words, across these copper wires. So the voltage to the right, the electrical potential at the right of this resistor is the same as the electrical potential at the right of that one, is the same as the electrical potential to the right of this one, and in fact is the same as the electrical potential on the right-hand side of the battery. Similarly, the left-hand side of the top resistor is connected by a wire to the left-hand side of the middle one, is connected by a wire to the left-hand side of the lower one, is connected by a wire to the left-hand side of the battery. So the left-hand side of every single one of these has the same voltage, has the same electrical potential. Because the right-hand sides have the same, the left-hand sides have the same. The voltage drop across these is the same. So if I go around the lower loop once, I find a change in voltage of 0. And I'll start right here. As I go around the loop, I find a battery that adds energy. I find a resistor that takes energy out, and then I'm back to the loop, the end of the loop. But any loop is fine. So I can start at the same point, go through the battery, adds energy, go up the loop to the second one, and come back down again. I bypass the first one completely. In that, I went through a battery in the loop, and I went through the second resistor. Similarly, I can do the same. I can go through the battery, go through the third resistor, all the way around the loop. Battery, energy in, third resistor, energy out. Those are just energy conservation statements. Energy in equals energy out around any of the loops. So 0 equals that, equals this, equals this. But I know something about the currents, I1, I2, and I3. Conservation of matter just tells me the rate of electrons coming into this point is the sum of the 3 rates. In other words, I battery equals I1 plus the sum of I2, I3, because the rate of electrons that come out here is equal to I2 plus I3. If you put these two ideas together, you find out that I can replace all 3 of these with an equivalent resistance. 1 over the equivalent resistance is 1 over R1 plus 1 over R2 plus 1 over R3.